In this video, we're going to introduce iterative programming into our MATLAB tools for solving problems. We'll also get a general introduction to some more sophisticated programming features in MATLAB and programming languages in general. Our primary objectives are to introduce the basic programming concepts of sequential, iterative, and conditional execution. Sequential programming, this is basically what we've been doing all along. We'll use for loops to implement iterative programming control and understand when for loops are necessary in MATLAB, which is not nearly as often as another programming language, and learn how to vectorize code that is written as a for loop. And we will obviously learn what that term vectorize means and why it's important. So let's talk about programming flow control. So all along in this class to date, you've been writing computer programs, either script M files or function M files, that use sequential flow control. And what that means is that the commands in your code have just been executed one at a time in the order that they are written in the M file. There's other types of flow control that we might want to use as we get into more sophisticated problem solving or numerical techniques. Today, in this video, we're going to talk about iterative flow control, and in particular, for loops. So iterative flow control is where we want to execute a set of commands repeatedly. Either we might do that for a fixed number of times, and that's this week, here in week 8, or we might do that while a certain condition is true, and we're actually going to skip over to week 10 to talk about that type of iterative flow control. So we have two different types of loops. We call all of these loops because we're going to loop through a section of code multiple times. We also can have conditional or logical flow control, and in this type of programming we'll have the MATLAB choose which set of commands to execute based on the result of some logical test, and we'll cover that in week 9. So you see we have a few more topics in the course. We'll be spending the last few weeks focusing on this more sophisticated programming approach. So let's talk about a for loop. So a for loop in MATLAB has the following syntax. You use for some index, which is a scalar, which will be a scalar variable, equal to a vector. Note, this is not an assignment. Not necessarily an assignment in this case. We're not setting the variable equal, setting the index variable equal to whatever's in this vector. What the for command does is it will pass through each value in the vector as it executes the commands inside the loop. So here's the commands inside the loop, and for example, we will, for our first time through the loop, index, our index variable is equal to the first element, whatever the first element is of that vector. Second time, index is equal to the second element, and so on until we get to the last time. Then our index is equal to the last element. And so what's happening here is index is still a scalar, and what the for command does is cycles us through this loop, and each time through the loop that scalar variable index is equal to the next element in whatever this vector is. So let's look at a more concrete example here. So here's an example. Here we're just predefining some x, and then we have a for index equals 135. Then we have two commands, and everything inside the for loop is executed sequentially, just like what we've been doing to date. And then we always have to have this end statement. The end is required for for loops. Another note here is the indentation. The indentation will happen automatically with the mfile editor as you type in a for loop. It's considered best practice to indent the commands that are happening inside the loop because it helps to visualize as you're reading the code, makes it more understandable to see what is the set of commands that's being executed inside that loop. So let's see what's happening with this loop. So if we go through our first pass through the loop, the variable ndx will have ndx will be the first element in that vector, so it is equal to 1. So then x is equal to 3 times 1 squared, or 3, and sum x is equal to sum x, which its current value is 0, plus x, which is 3. So that's going to be equal to 3. Then our second pass, index is equal to the next element, which is 3. X is just a scalar, so we're going to overwrite the value of x, and it's going to get a new value. X is equal to 3 times 3 squared, which is equal to 27. And sum x, now this next time through, its value is equal to 3. That's the value from the last time through. So sum x is equal to 3 plus this current value of x, which is 27. So that's equal to 30. And then our third pass, which will be our last pass because there's only 3 elements in that vector. And so for our third pass, index will equal 5, the next element in the vector. X will equal 3 times 5 squared, which is equal to 75. And sum x will equal 30 plus 75, which is equal to 105, sorry. So at the end of this section of code, that's all we have left is sum x is equal to 105, and the leftover value of x is equal to 75 after the loop. And that's a key thing to recognize, those intermediate values. In this case, since x is a scalar that we're overriding each time with this command here, those intermediate values just go away, where x equals 3, x equals 27. We're not saving those for later. We're just overriding those. Another thing I want to point out here is note, again, index is a scalar, so that's why we didn't need a period with that exponent right there, because index is a scalar. Lastly, I want to emphasize that this vector can be created any way you want. So for example, instead of 135, we could instead use index equals 1 colon step increment 2 to 5 would create the same vector, or even index equals linspace 1, 5 with 3 elements. So we can create that vector. We know how to create vectors. We've been doing that for the last couple weeks. We can create that vector any way we want. The important thing that's new here is what the for loop is doing. So we're taking a scalar variable and basically looping through a set of commands as that scalar variable takes on the value moving through each element in the vector on the right hand side. One way to help visualize what's going on in a for loop could be to think of a flowchart, and we'll use flowcharts to compare these various types of programming flow control as we work through these last couple weeks. So here we have this section of the program for a for loop. Here's our previous commands would be up here. Then we come in, we set up the for loop, and then we check to see if the index variable has been exceeded or exceeded the vector, the length of the vector. If it's not, we'll execute the commands inside the loop. These are the commands inside the loop. Then we go back, we increment to the next element in the index vector. Make sure that we're not exceeding that, and continue until we get to the last element. And then after we execute the commands for the last element, after the index vector is equal to the last element of our vector that defines the for loop, then we move out of the loop and then to the rest of the code, the next section of the code. One thing I want to point out, and you may have noticed this, is that this for loop is not necessary. It's not necessary for this particular problem here. We can execute this exact same task, do this exact same calculation without a for loop. And actually what I'd like you to do is press pause on the video and take a minute to think about this and how would you do this exact same calculation. Remember what the end calculation was, is calculate x, which after, at the end of the for loop, x was equal to 75, and sum x equals 105. Those were our end results from here. X equals 75 and sum x equals 105. How would you calculate those using just the vector operations that we introduced a couple weeks ago? So take a minute and try that out. Pause the video, give it a shot, and then we'll continue. Okay, so hopefully you've taken a minute to try and figure this out on your own, but you should come up with the following result. We can do this exact same calculation with vectorized code, or in other words, using the vector operations we've already learned. We could define a variable a is equal to 1, 3, 5. To find x, that's just the last element of a squared times 3, and sum x would be equal to the sum of 3 times the elements of a, and we want to square each element. Note the period here is necessary because now a is a vector, and that is a vector operation, whereas before this was a scalar. That's a scalar exponentiation here, and here this is a vector exponentiation. So that's part of what we're talking about when we say this is now vectorized code. And actually what's going on kind of in the guts of MATLAB when we have a vector operation in this, like this sum function operating on the vector, and the vector operation here, is this is actually also called an implicit loop. Because in the guts of MATLAB, in the underlying programming of MATLAB, is the loop, like what's happening up here, is still happening, but it happens implicitly. But it is still more computationally efficient to use vectorized code. And so almost universally we would say vectorized code is much better. It runs more efficiently, which means quicker program execution, which might not seem like a big deal to you right now because everything that you've done in this class runs pretty quickly on the order of microseconds. But when you get into more sophisticated, larger computations, MATLAB scripts could take 10-15 minutes to run, and that can make a difference if you could program it in a way that only takes 5 minutes to run or 30 seconds to run. Also, it's generally more intuitive and easier to understand vectorized code, assuming you already speak MATLAB, which hopefully you feel like you're getting to that point at this point in the quarter. So as I already said, this can become very important when performing large computations. 2 reasons. 1, it's quicker execution, and 2, just the general length of your code. Your code has less commands. So again, that makes it easier to understand. So overall, vectorization is a key feature of MATLAB. It's one of the things that makes MATLAB so popular in engineering computing. So we might ask the question, well, when are for loops necessary? For loops are really only necessary in MATLAB in 2 cases. 1, when we're building a vector or matrix in which the value of later elements depends on that of earlier elements. That's impossible to do with vectorized code. And we'll see an example here in part 2. This video is broken up into 2 parts just so it's not too long. The other case is when we're using conditional programming to change scalar values based on the values of individual elements in a matrix. So the key here, you've done lots of conditional programming already, actually using implicit loops when we've had, say, relational operators in element addressing. Stuff like a greater than 0 equals 99. Those types of commands, that's doing implicit conditional programming. But this is tough to do when we're working with different size vectors or scalars and vectors. And we'll talk more on this later when we start talking about conditional programming. Next week. So that concludes this part of the video. We'll move on to part 2 and look at a case where the for loop is necessary.